Hi Year 12, this is our fifth lesson for the topic of vectors. In this lesson we're going to look at projections. So this is what we've learned so far. Geometric and algebraic operations with vectors, magnitude and direction, vector equations, dot product, and the angle between two vectors. So vectors can be resolved into their horizontal and vertical components, like this. If we have the vector u, then this is the vector u cos theta, and this is the vector u sine theta. And that's just simple trigonometry. And this is particularly useful if we want to split a velocity vector into its horizontal and vertical components for projectile questions. The scalar projection of a vector u onto a vector v is the magnitude of this horizontal component of the vector. So it's like the shadow of the vector. But of course, vector v doesn't always have to be horizontal. So we could use that formula, magnitude of u cos theta. But we actually know a formula involving cos theta, don't we? It's this one. U dot v is equal to the magnitude of u, magnitude of v, cos theta. Now, if I divide both sides here by the magnitude of v, I end up with a formula. Here it is. So this is the scalar projection. It's equal to u dot v divided by magnitude of v. When we take a vector and divide it by its magnitude, that's a unit vector. So I could simplify this as u dot magnitude of v. So there's our formula. Here's our first example. Find the scalar projection of A, which is 2i plus j, onto B, which is 3i plus 4j. Now here's the thing. Neither of those formulas appear on the reference sheet. So if you want to use that A dot unit vector B formula, you're going to have to memorize it. But here's my suggestion. Start with this. The scalar projection is the magnitude of A cos theta. Now if we want to then substitute for cos theta, this formula does appear on the reference sheet. We need to rewrite it for A's and B's instead of U's and V's, but this is A dot B, which is equal to the magnitude of A, magnitude of B, cos theta. And then if we divide both sides by magnitude of B, we end up with that formula. And B over the magnitude of B is the unit vector B. Either way, let's do the question now. We know what A is. That is 2i plus j. We need to form unit vector B, which starts by working out the magnitude of B, doesn't it? Magnitude is the square root of 3 squared plus 4 squared, which is the square root of 25 or 5. So here it is. This is A dot. There's 1 over the magnitude of B, and this is B. Now doing the dot product, 2 times 3/5 plus 1 times 4/5 gives me 6/5 plus 4/5, which is 10 over 5 or 2. That's the length of the projection of A onto B. Now here's a note. The projection of A onto B is typically not the same as the projection of B onto A. Example 2. Find the scalar projection of vector u, which is 2i minus 2j, onto v if the angle between the vectors is 135 degrees. Now this is an interesting question for a couple of reasons. Firstly, because the scalar projection is negative, which is possible. So let's start with our formula, which is the absolute value of u cos theta. Absolute value of u will be the square root of 2 squared plus negative 2 all squared. Square root of 8 or 2 root 2. And theta is 135. And we can see why this is going to be negative, because cos 135 degrees is negative. It's negative cos 45. So simplifying, I end up with negative 2. Now the second reason that this is an interesting question is because there's two vectors v for which this question works. Here's our vector u. We could have v along here, or we could have v up here. And in both cases, the scalar projection is negative 2. So what does it mean to have a negative scalar projection? Now, normally when I've been drawing these pictures, I've said, okay, here's vector u, and here's vector v.
And this is the scalar projection here. And they point in the same direction. Can you see that scalar projection there points in the same direction as u? But in this case, vector v points in the opposite direction. So if we have a vector u and a vector v pointing in opposite directions, our scalar projection will be negative. And when we add direction to the scalar projection of u onto v, we get the vector projection. And sometimes this is just called the projection. And this is what we can write, the projection of u onto v. And here's the formula. So this first part, that's the scalar projection of u onto v, and then we multiply it by unit vector v. Now, it's important that we multiply by the unit vector, not just vector v, because we don't want to change the magnitude.
Here's example 1. Find the vector projection of A, which is 2i plus j, onto B, which is 3i plus 4j. Now, it's the same question we did earlier, so we already know that the scalar projection is 2. So to form the vector projection, we are going to multiply that by unit vector B. So that's going to be 2 times a fifth, and then multiplying by vector B, which is 3i plus 4j. And so our projection of A onto B is 6/5 of I plus 8/5 of j. And if we have a look at it on GeoGebra, here's vector A, there's vector B, and here is the projection of A onto B. Example 2. Find the vector projection of the vector A, which starts at 1, -2, and ends at 5, -1, onto the vector B, which is 2i minus 4j. All right, just slightly more complicated. We need to start by forming vector A. But that's easy. It's just going to be 5 take away 1i plus -1 take away -2j, or 4i plus j. Now, I'm going to use that quick formula to work out the scalar projection. That's going to be A dot unit vector B. So let's start by forming unit vector B. Here's our vector B. The magnitude is the square root of 2 squared plus -4 squared, which is the square root of 20, or 2√5. So there's unit vector B. So our scalar projection is going to be A dot unit vector B. Let's substitute in. We get 4i plus j dot, and I have just expanded these brackets. So we have I on √5 take away 2j on √5. And doing the dot product, we end up with 4 on √5 take 2 on √5, which is 2 on √5. So there's our scalar projection, 2 on √5. To form the vector projection, we just have to multiply by unit vector B. And we've already worked out unit vector B. It is I on √5 take away 2j on √5. Multiplying through, we end up with 2/5 of I take away 4/5 of j. Now, there haven't been a lot of HSC questions on projections. Here's one of them. The projection of the vector 6, 7 onto the line y equals 2x is the vector 4, 8. The point 6, 7 is reflected in the line y equals 2x to a point A. What is the position vector of the point A? Now, it's an interesting question because you can actually completely ignore this first line and just use coordinate geometry. We're going to draw a scale drawing. Now, I know in HSC you don't get grid paper, but you can draw a scale drawing just on a blank piece of paper. The point 6, 7 is reflected in the line y equals 2x to the point 2, 9. That's point A. And the position vector of point A is the vector 2, 9, and so the answer is B. How easy was that? Now, some students might not have attempted this because of this word projection and assumed it was too difficult. Let's have a look at this anyway. The projection of vector 6, 7 onto the line y equals 2x is the vector 4, 8. And we can see that also from the diagram. But with multiple choice, it doesn't matter how you get the answer as long as you get it. So if you want to use coordinate geometry in a scale drawing, then do it. And here's another past HSC question, this one from 2022. The following diagram shows the vector u and the vectors I plus j, -I plus j, -I minus j, and I minus j. Which statement regarding this diagram could be true? So with all these sorts of questions, we've got to go through all of them. We'll start here. The projection of u onto I plus j. So I need to extend that a little bit, and there's the projection there. So we're looking at this vector here. Could it be the vector 1.1i plus 1.8j? And this is curious. This diagram is drawn to scale. So remember, this point here is 1, 1 because it's I plus j. So could this vector here be 1.1i plus 1.8j? No, it couldn't be. So A is out. Now let's look at C because we're projecting onto negative I minus j, which is this vector here. How do we project U onto that vector? We want the length of this shadow, but we want it in this direction. So it's actually going to be this vector here. Okay, could this vector be 3.2i plus 3.2j? No. So it's out. Let's try B. The projection of U onto negative I plus j, so that's here. So let's project that onto that vector. So we want this vector here. Could this vector be negative 0.4i plus 0.4j? Yes, it could. So B is our answer. Now there's such a thing as a vector projection that is perpendicular to a given vector. So if this is our vector V here, then this here is our vector projection, and this green vector here, that's called the orthogonal projection. Remember, orthogonal means perpendicular. Now it's really easy to work out the formula, because remember when we've got two vectors that meet at a point, the vector between them is going to be the subtraction of the two vectors. We look to where that vector is pointing, it's pointing towards U. So this vector here will be U take away U dot unit vector V multiplied by unit vector V. Now that formula looks horrible, but it's pretty easy to derive. So here's an example. Find the vector projection of A, which is 2i plus j, perpendicular to B, which is 3i plus 4j. Now we already worked out the vector projection. It was 6/5 of I plus 8/5 of j. If we want the orthogonal projection, we're going to do A take away this. So the mathematics is pretty simple. We want 2 take away 6/5 of I and then 1 take away 8/5 of j, which gives us 4/5 of I take away 3/5 of j. Okay, that's it for projections. Our last video on this topic is on geometric proof. Hold on to your hats.